Okay, good morning everyone. My name is Mark Proctor. I'm the co-creator of the Drools rule engine. I joined Red Hat I joined JBoss back in 2005. JBoss was acquired by Red Hat in 2006. And this is my 10-year anniversary in October. Yay! My talk today is going to be very example driven. Those who haven't done Drools should still be able to understand the essence of what I'm getting at. But I'm going to try and avoid all the technical jargon of what a production rule system is and what an agenda group is and what a priority queue is and all of the more general concepts, the technical concepts, and focus more on examples. And even if you're not a rule expert or have no experience with Drools, I'm hoping you at least understand the essence of what I'm trying to do. So I'm going to start with a very simple example, and it's the number guess. And what I've done is I've taken standard Drools examples you can check out from GitHub, and I've split them down into a number of sequences. And rather than I've done before when I cut and paste them in, I tend to disengage people that way. I just now run the different sequences. Each one has slightly more rules than the previous one, and I talk people through them. So if anyone doesn't want an example-driven, lots of code talk, feel free to leave now. Okay, so let's just check if we can. I will enlarge the font. Let's see if I should be able to. JJ preferences, because no one can read that, can they? No. Or let's see if I can just change the overall. Is that better? Can people read that? Okay. I think I can zoom in anyway for when I'm showing code. A little bit you'll need to see the console at the bottom, but I will read it out and I will zoom in on code because I can easily enlarge code areas. So let's start with number guess. So this is the Drools example project. It says Drools example on the top left there. And you can check this project out yourself, and each of these examples can be run in IntelliJ or in Eclipse. They've all got names down here under the Java package directory. And somewhere down here, and there are a lot of examples now, they keep building up, getting bigger and bigger, I put it under games. There we go, number guess. And it's very simple. Our classes, so we have the guess class, and I'll just zoom in on that, and it has one field, the value. So it's number guess. I'm going to guess what the number is. And of course, there is a random number. And that, again, has a single value. The generated random number that you have to try and guess. And for those who've played this game before, as you normally know, there are a number of set times, a number of guesses you can have. You have 5 guesses, and it'll tell whether you're high or low. And if you do it within the time, you win, otherwise you lose. So I'm slowly going to build this example up for you and show you how you can solve this problem using a rule-based approach to programming. So if you want to run this yourself, the example class is number guess main 1, and it looks up the session. So the session is our runtime interface to our engine, and it has a name here, number guess 1KS for knowledge session. And you'll see this string. The way it looks up the thing it's going to run is you have a meta file called a K module. I'm not going to go into too much about how we build and deploy and stuff because that could get bogged down. But in essence, everything you want to run, all the individual applications have a knowledge base. That is the collection of rules. Every knowledge base has a name. And from that knowledge base, you can access sessions. Sessions is sets of data that will be run against that knowledge base. And that also has a name. And then you can look up these things via name. So it's very declarative. So somewhere down here will be knowledge base KS1. And it specifies the package. The package is where to find the rules for that example. So I will find it, actually. As I said, there's a lot of them now. Here we go. There's the knowledge base one. I will zoom in on that. So there we go. Number guess KS1 KS. And you can see there's the package. So the package is where it's going to slurp up all the rules from. If you go down to the resources folder and you go to number guess there, you can see that's where it's going to get the rules from. So it's a very simple declarative system. You've got to find and run rules. That's all I'm going to say on deployment. I'm going to go back and run this, show you the rules. And it's very, very simple. I have a main. And the main will select the game rules. which means the game rules must already be in the system, which I'll show you in a second. And it will generate a random number with a max range. And all this one is going to do is show you what that random number is. So it's not the full example yet. We're going to lead up to this. And what I'm trying to demonstrate here is something called rule chaining. One rule will insert data, which allows another rule to select that data and execute some set of actions. In this case, it's going to print a number. So if I go back to the main, there's my session. And in the session, I insert my game rules instance. The game rules has the max range of the number range and the allowed guesses set as the constructor. If I just run this now, as of course if all my examples run, it's never a good idea to be finishing off your examples before you come to a talk, because you're more likely to break some of your other examples. But anyway, I have gone through and tested all of these. And that's all it's done. You can see the print statement there. Can I zoom into that? I can, great. So that you can see is the printing out of the random number, and the random number is 10. So again, the session holds your data. You can treat it like an in-memory database. You insert, you update, and delete data in this data store, and it's held inside there, just like a database, like an in-memory database. Rules, and I'm going to show you a little bit more about this in a bit, are they select the data because like a database. So the main is saying select the game rules, which we just inserted. And then it's saying insert random number. The show number rule is selecting the random number and printing it. It can only select it after it's inserted. Again, I'm not going to go too much about the mechanics of this. I've got small slides I'm going to show in a minute. I'm going to try and keep things more around the example. So now let's go to the next level of complexity. So we've seen we've got an in-memory database. We can select data. We can execute actions and triggers, and we can chain rules. One rule can insert data that another rule can select, react, and respond to. So number guess 2. So the same main rule. What we're going to do this time, let me just zoom into that, is I'm going to add a REPL command line to get the user guess. So once the random number is selected, and once the game rules is selected and the game, if you look at the top, the game is inserted elsewhere. It will see this line here. That's a little REPL, and the REPL will just wait for the number you're going to insert. And it will create an instance called new guess. This is the object that represents your current guess. And all it's going to do this time is that once a guess exists in the system, once you've inserted it, it's going to print out what your guess was, and it's going to tell you what the number was. There's no other logic in this. It's just showing you again this chaining sequence of rules, how if I insert data, how if I manipulate the in-memory system, how other rules will respond to this. So again, the only difference in this one here with the other one, that says 2KS rather than 1KS. It's going to go to a different configuration in the K-module file you saw. And I just run it just like a normal Java program. Run number as main. Very simple. Anyone can run this in IntelliJ. Oh, I did actually delete the game. I knew it. I was messing around trying to simplify things. 1 second. There we go. I thought that was missing. So the reason why that didn't do anything, because to guess the user, the game has to be inserted. There was no game in the system, so it couldn't select it, therefore the rule couldn't fire. Put that in there, and now the game will exist within the system, and I can run it, and it should work this time. There we go. So what's happened here is now that the game is in there, it's able to select all of the objects necessary for the rule to be able to fire. When the rule fires, it opens this print statement that you can see there. It creates a buffered reader, and a little REPL, and now I can put in a guess from 0 to 25. I'm going to say 15. It's down there, you can see I'm going to say 15. I'm going to press enter. Your guess was 15, but the number was 0. So, and it's even hard-coded. So you can see there's another mistake. No, that wasn't hard-coded there. It's the range. Oh, so it really did just come up with 0. Okay. Let's go on to number 3. So number 3 now is going to tell you whether your guess is higher or whether your guess was lower. So if you remember, when it first starts off, the main will insert a random number, a random generated number. And the get user, once the random number exists, because it can't fire until each of the objects it's selecting, each of those objects must exist in the working memory for it to select them, to create a row that it can execute the trigger on, to execute the action on. Once you've inserted something into the REPL, it creates your guess. Now that we have a guess, we can check whether the guess is higher or lower than the random number. And you can see this here. There's the random number, and there's my guess. And if the guess is greater than the random number, so V is the value of the guess, R dot value is the value of the random number. If your guess is higher than the random number, your guess was too high. And it's the same if your guess was lower. So now you've got a simple system to be able to enter guesses and to be able to check whether your guess is higher or lower. And notice this retract here. So what this tract will do is it will remove the guess from the system, or delete it, like deleting a row from the database. And if you look up here, you'll see not guess. That means that the REPL command line rule will be triggered by the removal of the guess, meaning once the guess has been removed, it's done the higher or lower check, it will circle back around and allow you to input another data entry. So now what you have is you have 3 different rules that will act in a circular motion. So there's a circular chaining. So I'm just going to run number 3. Oh, I should quit number 2 first. Okay, so now we're in number 3. So again, we're at the REPL command rule. So the get user guess. So again, there is no guess. We've not yet put a guess into the system. So it's printed out, the print statement there, and it's allowing you via the input buffer to put in a guess. So I'm going to put in 10. Your guess was too low. 20. Your guess was too high. 15. 13. There we go. So at that point, I must have correct must have got the correct guess. However, it didn't notify you. You didn't see anything that said you have the correct guess. So we need to put something in to check now that we knew when it was too low, we knew when it was too high, but we didn't know when it was the correct value. Now notice it broke the loop though, whereas before it kept on looping round and round and round. The reason why the loop was broken is because we didn't retract the guess. Without the retraction of the guess, without the removal of the guess, it won't loop back round to be able to go back to the REPL rule. So again, number 4. And number 4, here we go. So I've got a little rule here that will simply tell you when you've guessed correctly. So now we'll know when it's too low, too high, or equal to. Notice how each rule is separate from the other rule. It adds new information to the system, but it's completely self-contained. It does one thing. It detects a situation, and it informs or it executes an action on that situation. And this is very unique to rule engines or even databases which are related to rule engines compared to, say, Java code. You try to have isolated rules, each one of them doing a very small job, detecting when something happens, doing something when something happens. And here I have 3 rules. One rule will detect when it's too high, another row when it's too low, and another rule when it's equal. So I'm just going to run that now. I went through and removed the class from all of them, and I obviously didn't put it back in. So give me 1 second. It's that game. I obviously changed the insertion point. There we go. So we're back to the guess. So remember before, it checked when too low, too high, or equal to. So I'm going to put in 15 again. Your guess was too low. 20. Your guess was too low. 23. Your guess was too high. 22. 21. You guessed correctly. So you see how this exited differently from the previous one. The previous one didn't tell you whether your guess was correct. We've now added one rule, and we've added new behavior to your system by simply adding one rule. And notice that each rule is separate from the other rule. Okay, and now the final one, and then we're done on this example. I know this might be a slow pace for some people, but for other people this might be quite a fast pace. So I'm trying to go through the incremental steps, showing you how each rule changes the behavior of the system. So obviously the thing that is missing now is to count the number of guesses. There is the number of guesses is 5, depending on the game rules. And if you don't guess it in 5, you want it to exit out. So how do we do this? We add a rule here that says no more guesses. So when the guess count equals the allowed guesses, and the allowed guess is determined by the game rules, which is the first object you insert, then it will exit from the system. And you can see here in the get users, yes. So currently in this get user rule that gets the guess, it doesn't select, it will let you go on forever. If I go to number 5, I've added a new constraint. The new constraint means that this rule will only fire now while the guesses are less than the allowed guesses. So we've added constraints in to limit the number of guesses you can have, both on the times of the inputs, but also then handling once you've gone beyond the number of guesses to inform you about what is going on. And you can run all of these yourself. If you don't quite get what's going on, don't panic. You can download these and you can run each of the individual stages yourself. The last one was easy. You had an unlimited number of tries. This one's going to be a bit more difficult now. So you have 5 of 5 guesses left. So let's go. Number 15, your guess was too low. 20, your guess was too high. 18, guess too high. 17, too high. 16, yes, a 1. So that's it. So there's a complete game, rule-based game that is reactively driven. So if you notice, everyone keeps talking about reactive systems. Reactive systems are nothing new. Reactive systems are when I have changes of data, things respond to this. And this is what you have in here. Data is changing. The changes in the data are being detected, and rules are firing response to those. And the rules chain. That means that one rule will change data, the other one will respond to. When I put in a guess, it changes data. The other rules detect that, and they will respond to that, saying it's too high, too low, or equal to. This is a reactive system. This is a declarative system. Okay, it does get more interesting than this. So I'm just going to do a really small bit of a theory, just very, very quickly, for those who are new, just getting some terminology. So we have a rule, which you've seen already, that has a when and a then. When you detect a situation, then do something. This one should be obvious by now for what you've seen. We have this term called a pattern. A pattern is the object type, and then it's the constraints underneath. And you already saw this. This is the game rules. This is your guess. And inside of the brackets, you have your constraints. We call those patterns, and it's very similar to SQL. So I'm going to show you one example that will show you how rules matches to how SQL works. And this will help your understanding of what's going on in the rule engine. So I have 3 classes: account, cash flow, and account period. And I've got a SQL statement on the top left, and I have a rule on the top right. And it's very simple. This is going to select the cash flows for a given account period for a given account number, and they're going to be credits. When we have the when, and is this point to work? Yes, you can see the account there. So when it's saying from account ACC is the same as saying the account pattern here. That's the binding in the rule. This is the alias for an SQL statement, and it has the same behavior. And same for the account period. And here we have a literal constraint inside of rules, inside of DRL. The constraint is inside of the pattern. In SQL, it separates the selection of the object type or the table, the constraints, whereas we put them together. But the behavior is the same. So that one you saw was a literal constraint. This one is now a join. So you join across tables in SQL, you join across objects in the rule engine, and the behavior, how it selects the cross product, is identical. If you can understand an SQL join, you can understand how the rule engine works. And this is the date range. Again, there's the date range there in SQL. There's the date range there in rules. So if you understand SQL, you can understand rules. And now I'm going to show it more in an illustrative example. If people have been to my talk before, I do apologize. I show this every single time. But it does help people get an understanding in their own head if they're a little bit stuck with what's going on. So a rule is a materialized SQL view. It will materialize rows, and for every row that is materialized, it will execute a trigger. So here we have the rule for credit, and here for debit. Given this cash flow table, account period 1, it will materialize 2 rows, 2 for credit, 1 for debit. If you execute the action, if the trigger executes for the 2 credits and for the debit, you end up with a balance of minus 25. So if you understand SQL, if you understand materialized views, if you understand triggers, you pretty much understand the behavior of a rule engine. There is one caveat, though. There's one big difference. In a rule engine, in a database, you cannot mutate the data you select from. So when you run an SQL statement, when you have a materialized view, when the trigger tries to update the tables, if it updates the table it's selecting from, you'll get an error. In a rule engine, we have a way to deal with this because we separate the selection phase with the updating phase. And this is a necessary part to be how to have the rule chaining and to have the execution flow of a rule engine, which a database doesn't have. I won't go into too much for that now, but it's the one small difference. The other thing we have is priorities. So how do you choose the order in which rules can fire? When they have to go back here, these rules are all materialized at the same time. If all the rules materialize at the same time, which one do you fire first? In actual fact, the order shouldn't matter, but sometimes it might matter. In the case of being able to do a print statement, I want to do all my credits and my debit calculations first, and only do my print statement once I've done those. So how do I do this? I give it a salience of minus 50. So although all the rows of data materialize at the same time, it will execute them in a certain order. The first ones are arbitrary, because they'll all have a salience of 0, i.e. there's no particular order of them, so it will be arbitrary. This one has minus 50, so it will execute once all the other ones are done. In addition to this, actually, within Drools-6, we will order the execution based upon the order they appear in the file. So if you don't want to deal with put the salience values in there, there is an implied salience by putting the order of the file. And that can be quite useful, and I use that a lot through my examples. So this is how it gets around mutating tables. It does the insert, what we call the working memory action phase. Insert, modify, or insert, update, delete, or modify and retract. The terminology has changed over the years. This slide is old now. So it does the working memory actions, which modify the tables. And then it goes to the selection phase, where it will go to select one of the rules in which it will fire. And this is called the agenda evaluation phase. So it means it will materialize all the rows. It will select one row based upon the salience, which could be arbitrary or not. It will then fire that. And then when it fires it, it's back into the consequence, which means it can go to do more operations and go back up. If you're inside the working memory action phase and you do a delete, and there's a materialized row, which depends upon that object, the deletion of that will remove it from the materialized rows, and it will never fire. I don't want to get into too much of this today. I want to get back onto the examples. It's just a little bit of a theory. I can talk to them about that at the end if they have problems understanding that. It's a little bit hard to get your head around at first. This is the same thing if I move it to period 2, and it just shows there are no debits. There's 1 credit, and the balance is now 25. So, and we have a thing called a conditional element. There's lots of them. I'm just showing you the not one here, because you'll see this quite often in the examples. You've already seen the not conditional elements within the number guess. When there was no guess, do something. When it goes from 1 to 0, do something. Either was a guess, there is no longer a guess, do something, or when you start off and there's no guesses, do something. When there are no buses, no red buses, do something. When there is at least one or more. So now I'm going to get on to a slightly more real-world example. This is a new one, so if you've been to my talks before, hopefully you'll find this bit interesting. So this is a diagnostic car system. So this is a real-world chart you get from one of those books if you're a mechanic. And as you know, you have to go through this diagnostic system. I zoom in a second. Here we go. And you can see this is a real-world diagnostic system if I want to find out what's going wrong with the car. And what I've done in this example is I've taken one of the left branches and I have codified it into my rules with a little REPL command line so that I can diagnose cars. And this technique can be used to do any type of diagnostics. We have an application, well, it's a community one, done by an external company called Tohu, which has a more developed version of this question and answer system. So I'm going to run that now. And again, I've done it step by step, because this is quite a complicated one. Just going to show you the models. So you're going to have a question. The question is each of the nodes that you saw. Each of the nodes in the diagram will have a question. This one is going to be very simple. We're only going to have true or false answers. Obviously, a more realistic situation could have all sorts of different types of answers. But in line with the diagnostic picture you just saw, there'll be a true or false. So every question has an ID, has a text. Then there is an answer. So as you use the REPL command line, you can answer each question with a yes or a no. So I'll just zoom in again. So it's only two fields there. Only two fields there. The solution is when you go down the path, it will eventually get to a solution. There's no more stages below that path, depending upon the path you've taken with the yeses or the nos, and it will create a solution object to represent the final solution. And I've created a class that is a static helper for all the available questions. I call it won't start. There are only 4 questions here, and this relates to the left-hand side here. So if you actually look, there is 1, start cranks, 2, starter spins, battery read over 12 volts, and terminals, clean terminals. Those are the 4 questions that you need to know. From those 4 questions, we have a number of different solutions. Your solenoid stuck, not powered, missing teeth on flywheel. I know nothing about cars. I have no idea what this means. I know jump start. I know what a jump start is. So if your battery reads over 12 volts, jump start or pop start a car, check if battery is charging. So these are the number of different solutions based upon the 4 possible questions. I've encoded those questions as a helper class in these static member variables here. So let's go to the DRL. And again, I built this up stage by stage. Each one introduces new behavior. So you can run these yourself. And you can actually, as an exercise, you could go back to this chart. The link is there. And start adding more questions yourself, actually, and complete more of this example. Okay, so we have an init. This is my initialization rule. The reason why this is an initialization rule because it has no left-hand side. When there's no left-hand side, it's always true, which means it's the first. Which means it's the first thing. Is that better? Yeah. I can't read any of that anyway, so I have no idea how big that is. So the init rule is going to print out a text that says input yes or no, or ID to change the previous answer. Now, actually, in this version, you can't change previous answers yet. I'm going to build up to that. And I'm going to introduce a new, not a new, but a powerful concept for integrity management. And obviously, the first question was start cranks. And it's very simple. Inserts the question, start cranks. And then I'm going to have 2 rules that, so I've got one. Invalid inputs. Here we go. So when it first starts off, the only thing that exists is the question. There are no answers yet. So to get the answer, we're going to go back to the keyboard scanner, and we're going to ask for an answer. And it's going to be a yes or a no. I'm going to process that string. So you see this line here. The results of the REPL is going to return a string. But that string could be anything. So I'm going to need to process it. And I'm going to do that with a string match. So this is a regular expression. Because this string is inserted into the system. I can now select against it. So I select the string. We have the question. Now this bit is, remember you saw that not before. This bit is important because I want the question for which there is no answer. This will become more obvious later. So the moment when we have the init rule, it will insert question 1 and question 1 only. There is no answer for question 1 yet. So it will match the process answer, and if it's yes or no, and it will create a new answer for question 1. And it deletes the string. So the string is no longer deleted. However, if the string stays within the system, we know that it was not a yes or not a no. It was something else. We don't even need to detect what it is, because if this rule doesn't fire, this delete, what have I just done? This delete doesn't execute either. If the delete doesn't execute, the string is still in there. So that means my invalid input can still fire for the string, for the question. And what it will do is it will remove the question from the system and put the question back in for the system, and that will re-trigger the ask question here. So let's just run this now. So it's not the whole example yet, it's just literally just showing you the REPL command, a little bit similar to what you saw before. So I'm just putting rubbish in. And it's just telling me it's rubbish. And I'm going to say yes. And it just repeats. What that does there is I put yes. So start cranks yes. And I'm going to show you what happens if I do no. Just run it again. And I'm going to go back to the rules so you can understand what was happening there. 1 second. So just rubbish. Press N. And now it says start cranks no. So let's go back to the rules. And if you look here, let's move this down a bit. If you remember before, the system starts off, we insert one question. There's a question, but there are no answers. The little REPL rule takes your input, validates it, only when it's valid, we'll create an answer. So now we have a question, we have an answer. The question can have two states. It can be yes, or it can be no. So if the answer is yes, it will select, it will materialize the row, and it will do this print here. If the answer is no, it will select, it will materialize the row, and it will print cranks no. So this is showing you how you can put in your answer and select a different branch depending upon the answer. So now let's build this up a little bit more, work more towards a real diagnostic system. So the init rule creates question 1. We haven't seen question 2 yet. How do I do question 2? So if you remembered before, let's just zoom that in. I had start crank yes and start crank no, and all I did was a print statement before. If it's yes, I do a to-do here. Why have I done that? Because that is the right branch of the root node, which I haven't inputted yet. So for those who don't understand what I mean, start cranks here. If it's yes, it's going that way. I haven't encodified that right-hand side. So it will just exit. We'll do nothing. That's an exercise for someone to come in to fill in the to-do to drive the questioning system there. So I'm going to go back. So start cranks is the first question. If I answer no, it should ask another question, starter spins. So we're going to go back. If it's yes, it's just going to halt the system. That's not codified yet. If you answer no, it just puts in a new question. Again, this is an example of rule chaining. I do my init. My init creates my question. That allows my REPL to do something. My REPL inserts something. That now allows my, depending upon the answer, to select the starter crank no rule. That creates a new question, and now we go back to the REPL again. So we have this rule chaining process. The data drives the rules. So I now add in 2 more rules to process starter spins. If you answer yes for the second question, you now get a solution. If you answer no, I'm not going to codify all the rules quite yet. I'm building it up. It's just going to do a printout. We're going to add more of those over the next section. So all you've seen me do here is go from 1 question to 2 questions where the second question will provide a solution. I'm going to run that now. Everything else, just check in, is all the same. So if you remember, if I say yes, it's going to exit. So I'm not going to say that this time. I'm going to say no. Watch, I'll show you, just put some rubbish in again. Invalid. I'm going to say no. So it's gone to the second question now. So it's chained from the first question to the REPL to get my yes or no onto the second question. Now, I forget which one it is. One of these comes up with a solution, and one of them will do a printout. Let's go for the yes. There we go. I found a solution. That means it's got to the end of the tree. And that's what this is. This is a decision tree. If I'd selected no, it would have just exited out the system. And you can see here, solution found, solenoid stuck, not powered. Oh, that's one bit I didn't show you. Here we go. So how did it know when you got to the solution? This is a rule that was added to this example. And all it's doing, it's an end rule. And it detects when there's a solution, and it prints it out. So that wasn't there in the first one. So now we've got a way to chain down questions, put in questions and answers. When we get to the leaf, we can put in a solution. When we put in a solution, we can have a rule to print out the solution. Let's get on to number 3. I'm going to start to speed this up a bit now. Hopefully everyone's getting the hang of this. Number 3, just... Oops, there we go, number 3. I've got little bullet points there that says what this is. What we're going to do now is allow the ability to reset. Because if I fill in all these numbers, and I do yes, no, yes, no, yes, no, and I realize I've made a mistake, I need to be able to roll back. But if I roll back, I don't want to have to manually manage all of the individual questions and answers. I want the system to do this for me. So how do I do this? Well, first of all, I have to be able to detect a number because I want to roll back to the question. So I add in a new sequence 2. Where is it? Here we go. First of all, I want to see if it's a number, I have to say that it check if it exists. When the question ID does not exist, it will tell you the question does not exist because I have to be able to roll back to a question that has been asked that's in our current system. When I insert a number, it's going to delete the answer. Now, that's what it's doing. And I'm going to show the magic of how this then triggers the rollback. So if I have questions 1, 2, 3, and 4, and I want to go back to, say, question 2, I delete my answer 2. But what about the answers to 3 and the answers to 4? They're still all in the system, and also the questions we all inputted. So we introduced a new thing called insert logical. So you've seen the insert keyword. Insert means insert, update, delete, just like you would in a normal database. Insert logical means that when I create an object, it will only exist while the rule is true. If the rule stops being true, it will automatically delete the object. So if I delete this answer, if this answer is deleted, this question will automatically be deleted straight away. Now, if we have the question, if we, I did a cleanup rule as well. Where is it? Here we go. That means that we delete the question, but now that means we have answers without questions. So I need to have a cleanup rule. And that's what happens here. So anytime there's an answer now without a question, it's going to remove the answer. So what we have a system now that will maintain itself. It will cascade back up to the one that you wanted. It will cascade by the automatic removal of the question you selected. When the question is removed, it's going to remove the answer as a cleanup, and this will then cascade down because of the logical insert. It's a little bit complicated. You don't need to understand it now. I'm just letting you know that that's how this works. I'm going to run this now. So no, and then I'm going to go back to 1. And it's actually going to print out as well. It's telling you it's removed these answers. It's chaining back up because of the logical insertions. And I can repeat again. No, yes. And I'm going to go back to 3. So it's just removed 1 this time, so it's gone back to 3. No. There we go. Solution found. So now we have a diagnostic system for questions and answers with the ability to roll back, and you can have 10 or 20 deep trees, and the system will maintain the integrity for you, so you don't have to figure out how to do that automatic rollback via that little logical insertion you saw there. Okay. I'm going to go over this one very, very quickly. This is to try and show good rules and bad rules, and it's going to demonstrate a little bit about truth maintenance again. So you've just seen the logical insertion, and now I'm going to try and show you this in a more applied way. So I have a department that issue bus passes. They will issue a child bus pass or an adult bus pass, depending upon whether you are less than 16 or greater than or older than 16. And actually, it sounds very simple. That's all it is. If you're less than 16, you get a child bus pass. If you're more than 16 or older, you get an adult bus pass. 2 rules. I forget, there's something like 6 different things wrong here. If you were to write your rules like this would be considered bad practice. How can you go so wrong with something so simple? And that's what I'm going to try and explain now. You can also represent this in a decision table, but I have that in a different set of examples, but I won't do that now. It's bad because it couples the logic. Both the logic of when someone is a child, i.e. less than 16, and the logic about to issue children bus passes. Those are 2 separate conditions. One is a policy, and one is an action on that policy. So it's bad because it's monolithic. It's taking different types of logic and putting them together. Is it a child? Do I issue children bus passes? 2 different pieces of logic put together in the same rule. It's leaky because what happens, maybe this is not the case, but if I'm doing a compliance system trading, the rule that issue bus passes, maybe it's not allowed to know whether you're 15, 16, or 17. Now the person writing the rules to issue the bus pass is exposed to information that they don't need to know. They only need to know you're a child. They don't need to know whether you're 15, 16, or 17. They just need to know you're a child. But now they're exposed to maybe sensitive information. Obviously not in bus passes, but if this is a compliance system, it could be. It's brittle. What happens when someone moves from the ages of 15 to 16? You're going to end up with a child bus pass and an adult bus pass because of the inserts there. And we can improve on this. So I'm going to, first of all, show you how we can do this by separating the 2 rules into separate rules. So the first thing we do is going to create a policy rule. So the policy rule is to determine whether someone is a child or not. So we're going to create a policy if it is child and a policy if it is adult. And we represent the result of this policy with something called an inference. And that's just an object that wraps up the result of this. So when someone is less than 16, we represent that with an is child object. This is our inferred piece of information. If someone is an adult, is greater than 16, we create an is adult object, and that represents the result of that policy. Now, you can see this insert logical here, which you saw in the previous example. That means that when the person moves from 15 to 16, the is child inference will automatically be removed from the system. So you have this ability to maintain the integrity of your system, to maintain, as data changes, you don't have to worry about making sure everything's correct. The Now you have the department that's responsible for issuing bus passes, two completely different departments. They no longer need to know whether you're 15, 16, or 17. That information is not visible to them anymore. They just know that I'm a person, I'm a child, and if it's a child, issue a bus pass. This also has the advantage that you now have semantic encapsulation. We have said that if this is a child, when I go back to here, if I have age less than 16, that's just a mathematical expression. We as a human might infer that's a child, but imagine this gets a little bit more complicated. It's more domain specific, and you're looking at a mathematical expression. You probably won't know what the semantic encapsulation of this is. So that's why we take expressions, we wrap words around them so people can understand what is the intent of those symbols. So we give semantic understanding to the symbols. And we also now logically insert the bus pass for the adult and logically insert the bus pass for the child, because it means when they change from 15 to 16, it will remove the child inference and it will remove the child bus pass automatically. So you're not going to have any 16-year-olds with children bus passes. And this creates a chain. These logical insertions create a chain of objects. If any of the objects above the hierarchy is automatically deleted, everything below is deleted as well. And this is good because it decouples knowledge responsibilities, encapsulates knowledge, makes it semantics, and it gives robustness. It's robust to change. It gives you integrity. The other advantage of this is that you have much faster change times. If you have a previous system and the policy people would say, oh, you're going to change from children are now people above and below 18, they're going to have to send you a spreadsheet. You're going to have to look at the spreadsheet. You're going to have to update your rules. That's no longer the case. They have their own rules. They will change their rules. And you don't need to change your rules. So it means by having this separation, you limit the amount of change you have to do, which allows your system, your company to run faster. I'm going to introduce something here called JTMS. And if I have time, I'm going to touch on a very complicated example, but very cool. So JTMS is an extension to the truth maintenance, the logical insertions you just saw. And you can give a plus or a minus label, what we call a neg, to a logical insertion. So what does that mean? When I do a logical insertion, I can actually do a contradiction to this. A contradiction means that that logical insertion will not appear within the engine. So if I create this chain that you saw here, how do I undo a part of that chain? I want to be able to say to you, actually that child bus pass there, don't issue a child bus to it. But I don't want to change the other rule. I want to do a separate rule and undercut the logic there. So I write this rule here. Do not issue to naughty children. If the child is naughty, I insert logical child bus pass just as before, but I use the word neg. Now you end up with this. So I have a child bus pass object. It's logically inserted. It has a plus and a minus label. That means it has people that say it is true, people that say that it is not true. They're in conflict. Therefore, it will not appear in the system. Nothing can respond to that. So it's a way of embargoing, of contradicting, of stopping something actually happening. This can lead to some very powerful and some very cool functionality. This is something that is experimental within our system. No, damn it. I've lost some slides. One second. Damn it. Okay, I've got a website instead with it on, if that works. I wrote the slides out and they've just disappeared. Here we go. It was just a text representation of this anyway. Imagine I want to write a system to select apartments. And I come up with the requirements that the apartment I'm looking for must be at least 45 meters squared. And it must have 2 bedrooms. If it is on the 3rd floor or higher, it must have an elevator. Also, it must have pets. I have price requirements. I am willing to pay $300 if it's centrally located. I'm willing to pay $250 for the suburbs. I am willing to pay an extra £5 per metre squared for a larger apartment, and I'm also willing to pay $2 per metre squared for a garden. I'm unable to pay more than $400 in total. When I've selected my apartments, if I'm going to give it a choice, I will go for the cheapest option first. I will go for the presence of a garden second, and the largest is the final one. So again, I've written this up as an example, how you solve this problem. And I just want you to think for a second, so just go back to that. How would you code that in Java? How would you take all those different pieces of logic with your apartments and filter that information and then write the rules so they can be readable and be maintained? You can end up probably with quite a mess. So I've only got a few minutes left. So I have an apartment with an ID, bedroom, size, whether it's central, number of floors, lift, pets, what you just saw described. So this is the available apartments. Then in my example, I will insert 9 different departments. And these apartments. And it describes the ID. It's in the constructor order. So the ID, the number of bedrooms, the size, whether it's central, is all encoded by these constructor arguments here. I then insert them into the engine, and I click File Rules. When I first start off, I'm going to have a default rule. So my default rule is all apartments are acceptable to me. That's how I'm going to start off. All of those 9 apartments are acceptable. But I'm going to introduce this thing called @defeasible. I know this sounds like a terrible word. This is the proper academic term for what I'm trying to demonstrate here. This means that this default rule can be contradicted. Someone can say, a better word is it can have an exception. So this is my default rule. Defeasible means it can be defeated. It can be defeated by my exception. So I'm going to have an exception rule here. It must have at least 2 rooms. And if this rule is true, that I have an apartment with less than 2 bedrooms, this will defeat. It will provide an exception to the default. And you use the word here, defeats. All apartments are acceptable. So this is a way to start with a default rule that selects everything and have another rule that says, not these ones. These are my exceptions. And this is called skeptical reasoning. And it's actually very hard. If anyone's ever done a pricing system or a trading system, you don't have all the information. And you start with default rules, and you try and add more rules, and then you try and add rules on top of the rules. And whether you do it in Java or whatever. And it gets difficult very quickly. I'm going to run this for now. And it will just print out all the acceptable apartments. And it won't have, I won't show you them all now, but it will show you all of them that are above 2 bedrooms. And notice the neg here. The neg is important. That allows me to, the defaults is positive. They're all acceptable. And the neg means it's not acceptable. I then go to number 2. I'm not going to run each of these. I'm just going to talk you through them. You can run these yourself. Well, I've just finished this one last night, so I'm going to put this up to GitHub, and you better run this yourself. So now I can encode each of the different pieces of logic you saw online. It must have at least 2 bedrooms. It must have at least 45 meters squared. It must allow pets. It must have a lift if above the 2nd floor. It must cost less than 400. Every rule is separate and every rule is atomic. I started with my default rule. All flats or apartments are acceptable. And now I have my exceptions. Whenever exception occurs, it will remove that acceptable apartment. So we have a nice way to have your logic isolated and separate and clear. So if I was now to run this, it would then show even less number of flats available. I'm going to go to number 3. And I now want to create offers. So if you remember, I had a rule that said, if it's central, I'm willing to pay an extra 5 per meter squared for garden and for the size of the flat. And if it's not central, I'm willing to start at 250. So this is rules to create my offers. Now I have to match my offers to my acceptable apartments. So those are my offer rules, and now here's the next new one here. The price must be affordable. Obviously, if I make an offer, that offer must be greater than the price of the flat. Otherwise, I need to exclude it. So again, here's all of my apartments. Here's all of the offers I've ever made. If any of the offers are below the price of the apartments, I'm going to logically insert that it's not acceptable. So this is another way of deselecting acceptable apartments. So first of all, we had exception rules to remove them based upon the initial criteria. Now we've had more exception rules to remove acceptable apartments based upon pricing. And now we want to do is find the cheapest, the largest, with the largest internal size and the largest garden. And that's what this rule does here. This one will find the cheapest, and it'll create an object to represent the cheapest. This one will find the largest. So if all the acceptable ones have not been contradicted, they've been left in the system, they have no exceptions to them, it will find the largest and the one with the garden. That's got the wrong word in it. Ignore that. I'm not going to run it now anyway. And then finally, I might come up with a conflict set. I'm going to have a number of these which are the cheapest, that are both cheap, large or large garden. How do I select them? Now, if you remember, we had a priority. We said that the cheapest is the most important. And I've got this the wrong way around, actually, I think. Defeats. Yeah, it doesn't matter. It still results. So I'm saying now that, the cheapest is the least important if it's cheap with a large garden. So no, it is correct. So if it's cheap and has a large garden as well, that will defeat R1. So the selection for R2 will win. If it's cheap with the largest garden and the largest internal size, that will win. It's controlled by this defeat. So one rule, again, you've got another, the default is the cheapest, and then I have my exceptions. Well, I want to have the one which is largest garden. One last bit, and then I'm finished. You've seen how you have a default rule, and you can have exception to your default rule. You can have an exception to your exception. You don't have to get all of this. It's just, this is really very, very advanced stuff. I'm showing you a little bit of the R&D that we're doing that's coming out now. We hope to productize over the next year. So if you remember, I said that it must have at least 45 meters squared. I can add another one here that says must have at least 45 meters squared unless very cheap. And this one here, this defeats this one. So I have an exception to my exception that now re-allows, so something that I said, I'm not going to allow this one. Another rule that said, no, I'm going to allow this now. So you can end up with very powerful argumentation that is very difficult or is impossible to describe in Java. And the other nice thing about all of this is that eventually, and we'll have tooling for this, you can show graphs for this. So you can show the graphs of the argumentations for your defaults and your exceptions to your exceptions. And I think with that, I'm finished. Any questions?